There should be no doubt right from the get-go that calculating the pH of a weak acid is going to be more complex than calculating the pH of a strong acid. And that's because weak acids only partially ionize, whereas strong acids ionize completely. In a weak acid, a typical weak acid like this made up one right here, HA, if I put it into water, the hydrogen or the H plus will be transferred to water to produce A minus and H3O plus, but that reaction doesn't happen completely. And in fact, the reverse reaction can also happen, and it happens to a pretty large extent. So H3O plus can donate itself a hydrogen back to the A minus. So what are we left with here? Really, we're left with equilibrium. And just like we learned in the last unit, an equilibrium equation can give rise to an equilibrium expression. And I've written one here for this generic reaction. It says Ka equals the concentration of H3O plus times the concentration of A minus over the concentration of HA. A few things we should note. Number one, we call this Ka because we're referring to acids, but it's just like any other equilibrium expression. We still have products written over reactants, and we're leaving out things that aren't aqueous or gases. In this case, we leave out water because it's a pure liquid. Now, every weak acid has its own Ka value, and these are commonly tabulated, and you can look them up. So I have a bunch of different acids right here, all with different Ka values. You'll notice that the ones at the top with the Ka values that are 10 to the minus 2 are considered to be stronger acids than the ones at the bottom with Ka values of 10 to the minus 10. Now, I say stronger, but these are still all weak acids. It just turns out something like HSO4 minus right here will ionize a little bit better than something like phenol written down here at the bottom. But for all of these, their K values are less than 1. And so we always at equilibrium have mostly reactants and very few products. They don't ionize very well. So if I want to calculate the pH of a weak acid solution, I have to use that equilibrium expression to help me get there. Let's say we're asked to find the pH of a solution of hydrofluoric acid. And the very first thing we're going to do is put that hydrofluoric acid into water to see what's produced. Here we get F minus and we get H3O plus. I can set up an ice table like we did in the previous unit to look at what happens between our initial conditions and equilibrium. Here I start with 1 molar HF. I have none of these products. I'm ignoring water because it's not part of my equilibrium expression. I know that some piece of this HF, a small piece, is going to dissociate or break apart. And I know that I'm going to gain that same amount in terms of the concentration of F minus and of H3O plus. So at equilibrium, I'm left with 1 minus X for HF, X for F minus, and X for H3O plus. And this is a little bit more complicated than it needs to be, because right now I'm going to have to use the quadratic equation to solve this. That's not impossible. It's something you're all capable of doing, but do we have to is the question. And the answer is we're going to find out that probably we don't have to. We'll see why at the end. But the assumption that we're going to make in order to simplify this problem in the beginning is this. We're going to suggest that this minus x right here is so small, the value of x is so small compared to 1, that essentially at equilibrium, this is going to be equal to 1. Think of it this way. If I had $1 billion and you took $1 away from me, how much would I have? Essentially, I still have $1 billion. $1 is such a small percentage of my $1 billion that taking away $1 doesn't really change anything for me. So when I go to set up my Ka expression for this, Ka is equal to my products F minus times H3O plus over HF. I can plug in the given Ka value, 6.3 times 10 to the minus 4. I can plug in X for F minus. I can plug in X for H3O plus, and I can plug in 1 for HF. So essentially here, 6.3 times 10 to the minus 4 is equal to x squared. If I take the square root of both sides here on my calculator, the square root of 6.3 times 10 to the minus 4 is equal to 0.0251 molar. That's X. But more importantly, it's also H3O plus concentration. So if I want to find the pH of this solution, pH is equal to the negative log of 0.0251, which is equal to 1.60. And that's the pH of this weak acid solution. Before we move on, we need to make sure that this assumption that we made, that 1 was essentially equivalent to 1 minus x, we need to make sure that that was a safe assumption. We do that by checking what's called the 5% rule. And here's where the 5% rule comes from. If I take my F minus concentration and I divide it by my initial HF concentration and I multiply it by 100, that gives me what's known as the percent ionization. As long as that percent ionization is less than 5%, then our assumption that we made here is a good one. So let's do that calculation. F minus, which was also equal to our H3O plus concentration, we found it to be 0.0251. HF was initially 1.00. Multiply that by 100, and we get 2.51%. This acid ionizes at 2.51%, less than the 5% rule, which means that this assumption we made at the beginning of the problem was a good one, and our pH of 1.6 is pretty accurate. All right, let's come back together and do another practice problem individually.